In this video, we will tackle a linear regression problem whereby we will use it to do a prediction of the prices of mobile phones based on some criteria. Let's get into this. We'll do this using Jupyter Notebook. The first thing to do is exploratory data analysis, or EDA for short. First, we will need to import all the libraries that we need. We'll require pyplot from matplotlib, and we import it as plt, seaborn as SNS, pandas as pd, and train test split from model selection from scikit-learn. We'll also need standard scalar from processing module of scikit-learn, linear regression from linear model. You'll also need mean absolute error, mean squared error, and R-squared score from metrics of scikit-learn. Also, you require to filter out warnings that may occur when our program is running. So you execute that cell to make sure that you have all the libraries. For this exercise, we require a data set that comes from kaggle.com, and the data set is called mobile phone price prediction cleaned data set. There is a link to the data set. In the data set, there are several columns that we require: ratings, and it contains the ratings given by customers. We have the RAM size in GB or gigabytes. We have ROM in GB as well. The mobile size, or basically the screen size, in inches. We have the primary camera, basically the number of pixels. And then we also have pixels of the front camera, the battery power, the price, which is what we are going to attempt to create a model that will predict the price. We will load the CSV data file that has already been downloaded. The dataset is pretty clean, so there'll be minimal cleaning required. We will use read_CSV to read the file. So you just pass in the path to your file. We can use .head function to print out the first 5 columns of that data set. So as we can see, we have this number of columns and the top 5 rows. We can explore the data by first understanding the properties of all the columns. So we use .info function on that data set. Here we see that is a pandas data frame that you're working with 807 entries. We have 8 columns and the number of non-null entries in each column. And we see that here we don't have any missing values. And the data type for each column is indicated here. We have floats and integers. We can confirm the number of missing values that may exist. It's always a good thing to do. Make sure that you always check for missing values in any of your columns so that it doesn't break the algorithms that you are trying to use, or the machine learning algorithms, in our case linear regression. To check for missing values, we use isNull function, and then we call the sum function to sum up all the true values. When you run that, you see that for all of them we have 0 missing values, meaning that we don't need to take care of any missing values or trying to impute missing values. Next, you can check the summary statistics, which is very vital to understand your data. That's why we need to do the EDA. The easiest way to check summary statistics is use the describe function. So when you say data.describe, you'll get the summary statistics. So here, looking at this, we see that there's a summary for each column. We see that we don't have missing values. So we say the mean of the rating is 4.11, which is pretty good. And then we see the standard deviation minimum values, 25 percentile, 50 percentile, and 75 percentile, as well as maximum value for each column. Because we have numerical variables, we can check to see the correlation between different columns. So this one is easy. We just use .core function after data. When we run that, we get the correlation between different variable pairs. So we see, like, for example, rating and rating is 1, and rating correlated with RAM. We see it's 0.12. We see varying correlation between variables. We would like to visualize this correlation matrix. We'll use pyplot as well as seaborn. First, we'll need to specify the figure size. So the figure size, you just pass the dimensions 10 to 8. And then using seaborn, we can go ahead and use heatmap function and pass the arguments. First, the correlation matrix is called correlation underscore matrix. We need to annotation. Basically, we need the labels. And then for CMAP, we say cool warm. This is just a theme which you want to use. And then we need to say the line width, we say 0.5. And then we need to add a title in our visualization as correlation matrix. So that's how our correlation matrix appears like. And then we see our scale here shows that the correlation is from 1 all the way to -2. And the darker the color blue is, the higher, the lower the correlation. For example, here we see that the price versus the primary camera has a negative correlation of -2. And the one that has the maximum correlation is whenever a variable is correlated to itself. Next, we can use pair plot from seaborn for visualizing different relationships between variables. This one is pretty intelligent because actually goes and check for all numeric variables and try to check the relationships between them. So in this case, when I run this, we see the relationship between different pairs. And whenever a variable is compared to itself, we see we have a histogram which shows the distribution of individual variables. I think that's enough exploration that we can do to our data. There's a lot that you can do. And here, basically, you identify the issues with the data. For example, you might identify that there are some outliers or missing values that you might need to fix before going ahead and process the data. The next thing we do here is just to start doing our pre-processing. Because our data is fairly clean and we don't have to do any cleaning. So here, we'll first split our data set into two: features and target variables, basically independent variables and dependent variables. To get the dependent variables, we first drop price from data, and to get the dependent variable, which is our price, we just subset the data and pass the variable name price. And then to split the data set into training and testing set, what we are supposed to do is use the train test split function that we imported earlier from scikit-learn. Then we say xtrain, xtest, ytrain, ytest, and then we pass xy. Test size is 20%, and then we initialize a random state of 42. What this essentially does is it ensures that whenever you split, you always get the same sample points for training set and the testing set. So we execute that to get our training set and the test set. The next thing we need to do, since if you remember well, when we visualized the first 5 variables, we see that we have different values, for example, rating, and the battery power is actually huge, meaning that we need to scale this data so that we don't have very high values and low values. So first, we call standard scalar and we assign it to a variable called scalar. Then we'll need to transform the training set using the fit transform function or from standard scalar. And then for the test set, we'll simply transform it using the transform function. And now we have the scaled xtrain sets and scaled xtests. The next thing we do is to build our model or our linear model. Several steps when building this model. First, we will need to create the model itself. To create the model, we'll need to call the function linear regression. Then, using the fit function, we pass the xtrain scaled set and the ytrain. Then we execute that, meaning that now we have our linear regression function. And to use it to make predictions, we have to use the predict function, and we predict the y or the prices, and we call it ypred. We call the model that we initialized here. Then we call the function predict and then pass the xtest scaled set so that we get now the prediction. Remember, we already have the actual values. So when you predict, you can go ahead and compare the predicted values versus the actual values to see how our model performed. And that takes us to the model evaluation step. To evaluate the model, we will need to use several methods. We can use the mean absolute error, mean squared error, or the R squared. To do that, we imported all these functions from metrics of scikit-learn. So we just need to call the functions. To get the mean absolute error, we use mean absolute error function, and we pass the actual value of the test set and the predicted value of the test set. The same for mean squared error. We use the mean squared error and pass ytest and ypred. As well as for R squared, we use R squared score and we pass ytest and the predicted value of the test set. Then we execute that. We can go ahead and check what the values of mean absolute error, mean squared error, and R squared are. So you can just place that in a cell, in a code cell, and execute. Here we see that the mean absolute error is 10,005.4 and a very big value for the mean squared error. and for R squared is 43%. These results indicate that the model explains about 43.3% of variance in price, which suggests that while the model has some predictive powers, there is room for improvement. Because 43% being explained, that's not a very good model. So we need to explore other models that can be used. And to do that, we can use other improvements for linear models like ridge and lasso. So we can actually go ahead and do it. We can say from scikit-learn linear models, we can import ridge and lasso. We can also try something like a decision tree. And then, because we want to compare more than one model or different algorithms, we use ensemble to test more than one. And so basically you can say from ensemble, import random forest generator and gradient boosting regressor. Go ahead and execute that. The next thing, we want to initialize the models. Just like the way we initialized linear regression, we can have them in a library and pass all these models. So we can have linear regression, ridge, lasso, decision tree regressor, random forest regressor, and gradient boosting regressor. All these are different types of models that we would like to test on our price prediction model. So here, after initializing these models, we'll need to store our evaluation metrics for each model, so that we can select the best that there is among the ones that we use. So we initialize an empty dictionary, and then to evaluate each model, we need to use a for loop that will go ahead and fit the models, do the prediction using the predict function, and check all the parameters, the metrics that we are using to test the models. And to do that, we will use this bit of code here. First, what this means says that for each name and model from models.items, basically for each of these models, fit this model, but just saying model.fit. We pass X train scaled and Y train, basically our training set, and then create a Y prediction for each using each model, and then get the mean absolute error, mean squared error, and R squared using this mean absolute error, mean squared error function, as well as R squared score. After doing that, we will need to write the model evaluation, or basically the MAE, MSE, and R squared to this dictionary. Go ahead and execute. Because our data set is very small, runs quickly. Otherwise, if you had a very huge data set, it might take a bit of time to run. Now, we will need to look at our model evaluation. So the first thing we need to do is convert that model evaluation dictionary into a data frame. So we'll first convert it to a data frame and then transpose. We can visualize, have a look at it, how it looks like, and see what seems to work best. And looking at linear regression, it had a very big mean absolute error, as well as lasso regressor. But looking at random forest and gradient boosting, we see that it has pretty small mean absolute error. as well as mean squared error. And here the R squared, which is a score showing how much variation is explained by our models. We see that we see this one is 82%, and which is very good, 82% of variation being explained. And we see that gradient boosting gave us the best score, which means that we can stick to this and say that for the price prediction for the mobile phones, the best model is gradient boosting. You can do some other tests just to confirm this is the best, but for now, for this video, this is where we get to. And if you like the video, please remember to subscribe, like, and share my videos. Thank you, and see you in the next video.